So, we started looking at the two concentric cylinders with fluid in between, and we essentially calculated the velocity profile. That is all we did yesterday, right. And we also looked at the limit, how to take the limit of such a problem. So, that you know, if you want to talk about a thin film or thin gap, how does it look like. We will look at that a little bit more in detail. So, this flow is known as Taylor-Cuet flow. Okay. So, right, and we found that there is only one component of velocity, which was u theta, right, and then you found out an expression for that, which happened to be a function of r. The inner cylinder was rotating with certain velocity omega, which means if you look at, so this is r I, that was r O, u theta at r I is equal to omega r I, because omega was the angular velocity of the inner cylinder, u theta at r O was 0. Okay, so, if you look at the velocity profile would basically decay something like that you will have to actually plot and see, but that is what. So, I am this direction is essentially u theta, okay, it is not u z, it is the velocity that is perpendicular to the plane in which I am drawing. Okay. Now, this profile, okay, is not a very stable profile. In fact, what happens is that if you define something called a Taylor number, which is T A equals to R I times R O minus R I cube omega square divided by mu by rho whole square. What is mu by rho? Is the kinematic viscosity. Okay, dynamic viscosity by density. What would be the units of this thing, mu by rho? You have heard about kinematic viscosity? No? Okay, it's basically defined as the ratio of dynamic viscosity to the density of the fluid. Okay, and it's a very useful quantity, and it's like diffusivity in the, so you have heard about mass diffusivity, you have heard about thermal diffusivity, have you heard about? Okay, you will hear more about in the mass transfer and the heat transfer course, and this quantity is a analogous quantity. Okay, this is mu by rho is more like diffusivity, it is called mu by rho is called kinematic viscosity. So, what happens is that if this quantity is approximately 1700 or below, then whatever you derived is going to be the flow profile when you do it experimentally. Okay. But if it exceeds that, then this flow happens to be what you call unstable. In other words, you will start seeing more or different things. So, to illustrate that, so let's say let's just look at the gap now. So, I will draw it in the next page. Okay, so that's my R I, that's my R O. So, if I am increasing my Taylor number, which is defined in that particular way, so Taylor number just includes the what you call the inner radius, the gap, the angular velocity, and some fluid properties. So, let us say you are doing an experiment and you calculate this and it came out to be, let us say, less than 1700, you will see the flow profile exactly what you derived in the last class. But if it happens to be bigger than that, then the flow profile changes. For example, if I take a cross section, okay, a perpendicular cross section, and look at what is the flow that is going to look like, there will be a primary flow which will actually have a u theta, which would be like that, but it also develops a secondary flow. So, u theta will be there as a primary flow, and then it in addition it develops a secondary flow, and that secondary flow will have both u r and u z components, and the flow in fact looks something like this. And so on this side. Okay. So, that means the fluid is not only going like this, it is also trying to do rotate like that. So, I am just looking at a cross section, and you will see that there are like things are going circle in the in round and round. So, each of these are called Taylor vortices. Vortices, so when you say vortex, okay, you have some feeling of vortex, right? Vortex is something which is going round and round. So, here you see that the fluid element will actually start going in round and round. So, these things are called Taylor vortices, each of them. Can you imagine how a fluid element will actually be going? So, see, when it was less than 1700, it only had a u theta component. Okay. Now, I am saying that if I am looking at a cross section with a Taylor number greater than 1700, you would actually start seeing things going round and round, but in that is only a secondary flow. The primary flow is still in the u theta direction. So, what happens if this is a fluid element? It was originally going like that, but now it had to do a rotation. So, it would actually go like that, it would go like a helix. Okay. So, any section you look like, any section you take, if you only look at that radial cross section, it would look like a vortex, but in addition things have to go round and round. So, overall it would be a helix, but then this is how the cross section would look like it will form bands, and you can see that this has got u z component, u r component and a u theta component. Okay. So, all of them will come into the picture. Is that clear? Now, this is not the end. So, in fact, when you look at the experiment, you would see that if this is the gap, you will see that there are these bands kind of thing that has formed. So, each of these band would represent these Taylor vortices. They will be just arranged next to each other. It is just a representation. Okay, each of them. So, one vortex band, next vortex band, next vortex band it forms. Now, if you increase the Taylor number further, even this becomes unstable. Okay, so, then in addition, okay, so that is my inner and outer cylinder. Okay, that is my R I, this was my R O. So, this is this was the the one which you see on the right hand side, this was what known as the Taylor vortices, and the bands, these bands become unstable and the bands would look something like this. So, each of these bands will not just go in one direction like that, each of the band will start doing like this, go around. Okay. So, that is even more complicated flow profile. That is what is going to happen. I can further increase my Taylor number because it's essentially a property, it's a number that consists only of geometrical parameters and fluid properties. If I increase it further, that's actually going to give you a turbulent flow between the plates. This is not turbulent yet. Turbulent flow would mean that everywhere you are going to see huge fluctuations. This is still laminar. Okay, the flow is still laminar, but the flow has got all three components and there is nothing that's fluctuating. It's just that there is a some kind of a wave that you would see. In fact, each fluid element would act like a wave which is traveling. So that's what. So all these three states, the one which we derived yesterday, which is the primary state that happens, is a simple flow, which would mean that it has just u theta going round and round. That's also laminar flow. With further increase in Taylor number, you will start seeing Taylor vortices, which means u theta, uz, all of them are there. It will form bands. The flow is still laminar, and then further increase, the bands become unstable and will form some waves. Okay, the flow is still laminar, and then it forms turbulent flow. So there are 2-3 points that I want to drive from here. Okay, one is that we keep making assumptions, right? We say that, oh, I'll take del by del theta to be 0. I'll take my ur to be 0. Okay, are they always true? So in this case, it clearly says that it's not, right? With our assumptions, we could get only one of the flow states. If we were able to solve the equations fully without making those assumptions, then we would have been able to get any of these flow states. Okay, but we are not going to get that. So you can always question the assumptions that you make. Is that clear? Okay. Second is that it's the same governing equation, right? The differential equation that you started with, it's always same. It's just that you have gotten now 4 different solutions. Okay, and that's because the equation is a nonlinear equation, and a nonlinear equation is expected to have multiple solutions. So you are ending up with multiple solutions for the same governing equation, okay, because the equation is nonlinear. Is that correct? Understood? 2 points. Okay, one is the existence of multiple solutions. The second is actually questioning the assumptions that we make. Clear? Any questions? So the point is that you can do theory always, but you do need to see experiments. Okay, unless if you were not able to do experiments, you would not have seen any of these states. Okay, so it's really experiments that has actually given insight into what these flow profiles are. How would you do experiment if you want to see flow? You can take 2 cylinders, that's not a big deal. You can rotate one of them, put fluid, okay, and in order to see it, just put some particles. Okay, just the way when the particles are there, you can see that the particles are moving. Just like you can see or visualize how smoke is going. So the same idea is what is followed in an experiment also. You can take fluid and put particle and keep increasing the Taylor number. So let's see what that looks like. It is a nice movie. So you have 2 cylinders, okay, and one of them is rotating. You may not see much because it's just only the u theta. Okay, things are just going round and round. So you are not really seeing. You can, if you look carefully, you can see things moving, right? Can you see things moving? Now can you see fluid moving? So you can. So now, so you are not. So this is just yes. Okay. So this is Taylor number is very small. Okay, less than 1700. Now they will increase the speed of the rotating cylinder, which would mean that you are increasing the Reynolds number and the Taylor vortices start appearing. Okay, the square vortices that I talked about, they will look like bands. That's what you are seeing now. Okay. Now with further increase in the Taylor number, these bands will become unstable and it will start generating waves. So the bands become thinner and thinner first. there you go. So, the formation of the waves, okay. These waves is the third state that we discussed. So, the bands are forming the waves and the fluid elements actually are, they become traveling waves in fact. You can see that clearly now. And with further increase in the Taylor number, it is going to go to turbulence. So, this remember this flow state is still laminar. And now it is getting into turbulence soon. There you go. So, that flow is turbulence. You can see that there is lot of fluctuations in the velocity. You can see that all that nice structure is going away and it becomes very noisy. Okay. So, that is a turbulent flow. Now, what they will do is they are going to reduce the speed, and you can see that as you reduce the speed, that is equivalent to reducing the Taylor number, and it will go to these transitions again. So, right now it is all fully turbulent flow. Now, the speed is getting decreased. So, that means the Taylor number is going down. Okay. So, it has come to that state where you have waves of bands. Yeah, so that is about Taylor Cued flow. Okay.